So what I wanted to discuss today, shortly, are ways by which you can present classification results. And I'm going to look at this Wisconsin data. And in the lectures, we simply discussed a quantity which we call the accuracy. But this accuracy is just the sum over events which we classified correctly and divided by the total number of events. That means that if you have a binary class, we don't know how many of the positive events were classified correctly and how many of the negative ones were classified correctly. And that can actually be interesting, especially if you look at this Wisconsin cancer data, which ones were flagged as so-called true positive and true negative ones. And there is a quantity which is often used in this kind of discussions. It's called the confusion matrix or the error matrix. And that gives you an immediate and intuitive way of understanding how your model is functioning. And it can be useful. So we are not requiring that in the project itself, because we just mentioned the accuracy. But if you want to, with your prediction and the test data you are comparing with, you can just transfer that to a library, and then you can get the plot immediately. So it's just one line of code if you want to do that. And it gives a much more intuitive way of presenting data from classification cases. The normal case you will see this applied to is the binary classification problem, but you can extend this confusion matrix, which is meant, the reason of what's called a confusion matrix is that it's meant as a way to not make a confusion and to distinguish the so-called true positive and true negative results. And but before we do that, there are some simple ways of studying the data for a typical classification problem. So if you can plot the data, you should do that. And plotting the data can already, just by looking at the plots, can give you quite some insights about what the data are about. And another quantity which we discussed in the very beginning of the semester is something which is called the covariance and then the correlation function. So the correlation or correlation matrix is just the covariance divided by the variance. And that means that it will scale between -1 and +1. If things are strongly correlated, you get 1. If there is basically no correlation between two features, you will get close to 0 or 0 if there are no correlations. So let's just take a quick look. So what you will see here in the weekly slides for the exercise sessions is the implementation of a logistic regression case on the Wisconsin cancer data. And this data has been studied up and down for years, actually. And it consists of something like 500 people which have been surveyed. And they've surveyed something like 30 features for different types of way to classify tumors. And what you will see here, there is no scaling, nothing fancy. And one of the quantities which you can plot are actually the different features. And in this case, we are dealing with a benign tumor and a malignant tumor. So you can actually look at the different features and you can make a histogram plot of the bad cases and the good cases. And then you can compare and see if some of them can be clearly distinguished and others not. So just running this and plotting both the covariance or the correlation matrix, you will see something like this. So if you are a pathologist, if you look at this, you're just producing a histogram here. And in this histogram, you would present features like the mean radius. You have the mean texture. I don't know exactly what that means. I know what the mean area means, and I guess you also know that. And you would expect that there would be strong correlation between the mean area and the mean radius. If you think of a circle, I mean, the area is just pi squared times, not pi times r squared. So we would expect strong correlations there. So if you look here, you would now see that there are some features where there's a clear distinction between a good and a bad case. And then you have other features which are more difficult to distinguish between. So a pathologist or the medical team they know what these different features mean. So I would not be able to tell you what, let's say, the compactness means. I do understand that if the tumor is small, it could happen that it's a benign one, because it's a small one. But I'm not able to judge what the medical terms actually mean. So this is more a topic for the domain specialist. In our case, in the training here, we are just looking after whether we can classify correctly, whether this is a good case or bad case. So this is just one way you can display the data immediately, and that gives you some basic feeling. Then the other quantity which is useful to look at and which you can produce immediately is this covariance matrix based on the data. And let me just bring this up a little bit. So in this specific case, what you have along the diagonals, this is the covariance divided by the variance, and this has to be 1 along the diagonals. So here we plot the mean radius against itself, so that's 1. But if you look at this one, this is the mean radius against the mean area. And if you look at the perimeter, which is also proportional to the radius, you see a strong correlation. So this is often used in a method which we will not have time to discuss this year, which is called principal component analysis. And in principal component analysis, you use that as a way to reduce the dimensionality of the problem. So the covariance matrix, when you diagonalize that one, that gives you the variance divided by the variance, 1. And the diagonal elements can be used then to reduce the number of degrees of freedom by saying that those which have a small variance are results or features which we take out. So you could reduce from 30 features down to 10 features. And that would make the neural network training much easier. And if you have a number of features like 100 to 1,000 or something like that, then it's very easy to actually diagonalize this matrix. And then you can simply keep those features which have the largest eigenvalue. And simply say, these are the degrees of freedom I'm going to take with me when I now do a machine learning method like a neural network. So this is one way to do dimensionality reduction in an unsupervised way, because you just diagonalize the matrix and then you keep those features you think are most relevant. But this is also something which gives you a kind of feeling of which features may be important or not. And it's something which is very useful to do irrespective of machine learning method. So one thing, if you can, always look at the data. We actually in Norway had a serious case of scientific fraud. There was a medical doctor who had faked basically all the data, and they had received millions of funds, millions, for research on cancer in the mouth. All the data were faked, every image on the PhD, and the data which was analyzed by people who signed that they'd done the data analysis, actually this guy forged the signatures of the co-authors. When people looked into the data file, they would see the same name popping up again and again. And the only thing they had changed was actually the data on I don't know exactly what they looked at, but the data were just slightly changed and tuned so that you would reach a specific conclusion. This guy had even as co-authors, because this guy was a dentist, had even as a co-author his secretaries in the dentist lab. So that was a serious case of scientific fraud where everything was faked. But a simple look at the data file would have discovered the faking immediately. So always look at the data. That's if you can. So the quantities which we are going to look at now, besides these things, is actually a quantity like the confusion matrix, which gives you a very intuitive way of displaying data. So what you would define then are some specific quantities. So you have a number P, which simply sums all the positive cases, and you have to decide what is a positive case. What you will often see is a positive case in this kind of medical surveys is you having a malignant tumor. I wouldn't call that a positive case. I would actually call that a very negative one. But in this case, you can see if you look down here, true positive, sick people correctly identified as sick. I would actually call that true negative, but this is up to you. So you just simply have to decide what is true or false or 1 or 0. And one of the quantities you will see, which is being used widely, is true positive. That represents what you have classified as positive results correctly. And then clearly that leads to true negative. This means the positive results which you have classified wrongly. And sorry, the false positive. Sorry, not the true. The false positive are the numbers, the positive ones which you have classified wrongly. The true negative ones are the cases which are negative, or if you have 0 as an output, which you have classified correctly. And then you would have false negative, which is often also called a type 2 error. That indicates if a negative test has been wrongly classified. And if you think in terms of an illness, this is often the way you would see this being presented. So a true positive, sick people correctly identified as sick, false positive, healthy people incorrectly identified as sick, and so on and so on. So these are very intuitive ways of displaying the data. And if you want to use that in project 2, for the classification case, it's just 1 line of code. So it's pretty simple to do that. Now, there are other quantities which you will encounter because they are used to present data. So one quantity which is often used, and I have to admit myself that I always have to reboot my brain here because I don't often find this intuitive. I actually find it intuitive to look at the previous case, but if you just rethink a little bit the words here, one of the quantities which people often present is normally called the sensitivity or the hit rate or the true positive rate, TPR. And that is simply the sum over the correctly classified divided by the true positive plus the false negative. And it's meant to define positive results which occur among all the positive samples available during the test. And then there are other quantities like this miss rate or false negative rate. There is a quantity which is called the selectivity. And the selectivity is then the probability of a negative test result, which is conditioned on the individual truly being negative. And this is normally defined in terms of this Tn plus Fp. And these are typical quantities which you would see in many presentations of classification data, in particular binary cases, which are the most common ones. So you often have cases, you not paying your credit card debt, yes or no, I mean sick, yes or no, etc., etc. These are the most common cases. And what you will often see is that this TPR, the true positive rate, is often plotted against one of these other quantities. And one of the quantities is just like the false positive rate. And you have other quantities like the positive predictive value, which is given by these quantities, the negative predictive values, etc., etc. So sometimes, and this happens with the, so I'm just not going to go through all of them, but you have a quantity like the F1 score, which is also widely used. And this is something which you would use in case the data is very skewed, which means that you have more data on, let's say, the bad case than on the good case, or the positive than negative. So often, and you will see that with the Wisconsin data set, is that there are more of the positive, which means having cancer, against the negative case. So these are also things which you have to take into consideration when you use these quantities, whether there is more of one type of data than the other one, because then you would have less training data for, let's say, the positive case. So these are all quantities which you can find listed, and there are tons of them. And you should feel free to just explore these quantities. For us, in this project, it's enough to look at, let's say, the confusion matrix, or another quantity which many people like to display is something which is called the cumulative gain. And I will just show you examples on how you can do that. So another quantity which is used is this quantity from, it actually comes from electronics. And that's why it has this name, receiver operating characteristics. And it was actually introduced back in the 40s in the last century. And this plots the true positive rate against the false positive rate. And then we have another quantity which is called the cumulative gain curve, which plots this true positive rate against what's called the predictive positive rate. And that represents simply the fraction of positively predicted samples. Now, if you want to implement these things, if we go back to this cancer data, the only thing you need to do is have an import of this package scikit-plot. And then we run the logistic regression and make our prediction here. And if you want to plot the confusion matrix, the only thing you need to feed in are the test data you have and your prediction on the test data. And that's it. If you want to plot the ROC curve, you would then simply call this function, and then you can do the same thing with the cumulative gain. So these are very straightforward and simple implementations of another way to visualize the data. And if you look at so let me just bring up the confusion matrix. This is normally the quantity I like to study, because I think this gives me quickly an intuition about what is going on here. So let me just bring that one up. Actually, okay, so what you would have now would be the true positive here. And this is the false positive. So the fit here was 94%, that's the accuracy on the whole data set. But you see now I have a better one on the positive one than on a negative one. And I don't remember what was negative and positive actually. I always have to look it up. I think positive is actually having a bad tumor. So you see now that would be the true positive and the false positive. This would be the false negative and the true negative. So then you break down the data in something which is more intuitive to look at. So if you wish to, this is something you could actually add to the project. And then you have the ROC curve. So in this case, the ROC curve is a quantity. So let me just try to decrease. Oops. I actually wanted to have that one. So if the true positive rate is 1, that should give you the best possible model. So this shows you the ROC curve. So this is the true positive rate against the false positive rate. And if you look at the midline here, this is just you performing random guesses. So if you do toss your coin on a binary case, this is what you would get, the straight line in the middle. So this is random guessing. So ideally, you want to have a true positive rate, which is exactly equal to 1. Another curve, which is much used, is a cumulative gain. And that is an interesting quantity because it shows you this as a percentage of the sample. So you see now, if you have 500 data points and you take 20% of the sample, so one of the cases has more data and it starts classifying better, whereas the other one has less data. And when you now are up to something like 60%, then you see that both of them are getting close to a true positive rate, which is close to 1. So this is also very interesting because it shows you how your model is functioning as a function of the data or the percentage of the sample which you have, which is also very useful. So these are kind of insights which many people like to see when you present a classification problem. The one which I normally prefer is actually the confusion matrix. And that normally gives me a quick and intuitive view on how you're doing with the classification. And it also tells you that probably the data is pretty skewed, that there are more of one data set than on the other one. So that was about the things for the project, which could be interesting to do. And it's just 1 or 2 lines of code here, which you can easily implement. Now, the other thing I wanted to say something about is when you're writing the report, and we mentioned last time that you can easily use ChatGPT if you need inspiration for writing, let's say, the abstract or the introduction. And that is something you should cite, however, that we use that as an inspiration. So one thing which ChatGPT is very useful for is that you can have a conversation and you can use that as a scientific body. You ask a question, so you can think of like you asking questions to many people here, and then you collect all the answers, and then you synthesize an introduction, for instance, based on all these views. And this is the way we would work scientifically. I would read many articles, and I would find a statement from that article or that one, and I would use these in one way or the other ones, and I would cite them. So if you're using ChatGPT, you should mention it, that you have used it. And one thing you could do is you could even print out the conversation, because ChatGPT is actually a probability distribution, which every time you call it, it generates new outputs. So you could just take a screenshot of the output and put it on the GitHub page and say that I was inspired by this discussion. So you can look at ChatGPT as a body where you ask questions. I mean, what does a neural network mean? How do I write an introduction about neural networks? And then you can get ideas. That's a very efficient way of working, and it triggers also your creativity, because it will give you references, and if you have time, you can read the references, and that gives you more ideas and new ideas. So in a way, view it as a kind of body you can just ask questions to and get inspiration from. However, if you take a whole text which ChatGPT generates, and you put it in as your abstract or your introduction, and you don't cite anything, that would be scientific cheating in a way. It's like if I take a text from a scientific article and I just use that as my own introduction without citing anyone. That would be cheating. That would be dishonesty. But so it's important to discuss these things, because the university has no clear rules about how to use these things. And you should see this as a useful tool to generate things which you can use then to, trigger your creativity. Because this is at the end what we want with these reports. I mean, we want them to trigger your creativity. That's the whole idea behind our project-based learning, and also the kind of insights we want you to gain are insights which you normally would not have gotten if you were not to write your own programs. So if you have questions about things like ChatGPT, how I should reference it and so on, just ask us. But think of this as a useful tool in drafting a project. And also many of you have never written reports before. And most of you are also not familiar with English or scientific English, which means that to see examples is extremely useful. I did that when I started to write my first scientific articles. I looked at other scientific articles, and I did the kind of monkey see, monkey do, right? That's what I did. I'm still a monkey in free fall, by the way, according to my wife and my daughter. There is no learning here. Okay, so this was a little bit about ChatGPT, and I hope you will find this tool useful. It is just one good tool as many other ones. And if it can increase our scientific creativity, we should use them. But also keep in mind that we had people in the previous project which took text from articles or from lecture notes without citing it. You should cite the things you use. That's important, because that's what you would call a good scientific conduct, that you cite what other people have done. Questions about these things? So gradually, everybody's getting feedback now. We're uploading the feedback. So, and I hope that can be useful. And by the way, the last thing, before the deadline, we always get some mails, actually quite many, about possible extensions. So I am a pretty weak person when it comes to say no. So we will have a small extension till next Friday, if that is okay. I'm going to send a message to everybody, and you will also see that on Canvas. Okay, I will stop.